Welcome to Atomic Structure. In this chapter, we'll explore the particles that make up atoms, how electrons are arranged, and why atomic structure is fundamental to understanding all of chemistry. Course context and importance of atomic structure, chemistry specification overview for atomic structure. Atomic structure is a foundational topic because it underpins nearly every other area of the specification, including bonding, periodicity, energetics, and redox chemistry. The chemical properties of elements are determined primarily by the arrangement of electrons around the nucleus, making an understanding of atomic structure essential for explaining trends across the periodic table. This section is divided into three main areas: fundamental particles, mass number, and isotopes, including mass spectrometry and electron configuration with ionization energies. Development of atomic theory over time, basic structure of the atom, fundamental subatomic particles. Dalton's model, early 1800s, described atoms as indivisible solid spheres, successfully explaining laws such as conservation of mass but failing to account for subatomic particles. The discovery of the electron by J. Thomson in 1897 led to the plum pudding model, where negatively charged electrons were embedded in a sphere of positive charge. An atom consists of a tiny, dense nucleus surrounded by electrons in shells and subshells. The nucleus contains protons and neutrons, collectively known as nucleons, and accounts for almost all of the atom's mass. Protons carry a positive charge, while neutrons have no charge, giving the nucleus an overall positive charge. Electrons, which have a very small relative mass, occupy the space around the nucleus and are responsible for the atom's chemical behavior. The three fundamental subatomic particles are protons, neutrons, and electrons. Protons have a relative charge of +1 and a relative mass of 1, and they are located in the nucleus. Neutrons also have a relative mass of 1 but carry no charge, contributing to nuclear stability by reducing repulsion between protons. Electrons have a relative charge of -1 and a negligible relative mass of approximately January 1836, and they occupy orbitals around the nucleus. Atomic number and mass number, isotopes and their properties, relative atomic mass and weighted mean calculations, principles of time-of-flight mass spectrometry, interpreting mass spectra. Atomic number, symbol Z, is defined as the number of protons in the nucleus of an atom and uniquely identifies an element. In a neutral atom, the atomic number also equals the number of electrons. Mass number, symbol A, is the total number of protons and neutrons in the nucleus. Isotopes are atoms of the same element that have the same atomic number but different mass numbers due to different numbers of neutrons. Because isotopes have the same number of protons and electrons, they have identical electron configurations and therefore the same chemical properties. Relative atomic mass, R, is defined as the weighted mean mass of an atom of an element compared with 1/12 of the mass of an atom of carbon-12. Because most elements exist as a mixture of isotopes, their relative atomic mass reflects both the mass and the abundance of each isotope. Time-of-flight, TOF, mass spectrometry is an analytical technique used to identify isotopes and determine relative atomic mass. In a TOF mass spectrometer, atoms are first ionized, usually by electron impact, forming positive ions. These ions are then accelerated by an electric field so that all ions gain the same kinetic energy. The ions enter a drift region where they travel towards a detector. Because all ions have the same kinetic energy, lighter ions travel faster than heavier ones and reach the detector first. The time taken for each ion to reach the detector is measured and used to calculate the mass-to-charge ratio, m/z. The resulting mass spectrum shows peaks corresponding to different isotopes, with peak height or area representing relative abundance. Mass spectra display the relative abundance of ions plotted against their mass-to-charge ratio, m/z. For elements, peaks usually correspond to isotopes with a charge of +1, meaning the m/z value is equal to the isotopic mass. Electron shells, subshells, and orbitals, electron configurations up to Z equals 36, first ionization energy, definition and equation, successive ionization energies and shell structure, ionization energy trends in periods and groups. Electrons in atoms occupy energy levels arranged into shells and subshells, which are further divided into orbitals. The first shell contains 1s subshell, the second shell contains 1s and 1p subshell, and the third shell contains s, p, and d subshells. Each orbital can hold a maximum of 2 electrons with opposite spins. The s subshell contains 1 orbital, p contains 3, and d contains 5. Electron configurations for atoms and ions up to krypton, Z equals 36, includes understanding how electrons are removed to form positive ions, always from the highest energy orbital first. For example, sodium has the configuration 1s squared 2s squared 2p 3s to the power of 1, while Na is 1s squared 2s squared 2p. First ionization energy is defined as the energy required to remove 1 mole of electrons from 1 mole of gaseous atoms to form 1 mole of gaseous 1+ ions. Ionization energy provides evidence for electron configuration and the arrangement of electrons in shells. Factors affecting ionization energy include nuclear charge, distance of the outer electron from the nucleus, and electron shielding by inner shells. Successive ionization energies refer to the energies required to remove electrons one by one from the same atom. Each successive ionization energy is larger than the previous because electrons are being removed from increasingly positive ions. A very large jump in successive ionization energies provides evidence for the existence of electron shells, as it indicates that an electron is being removed from a shell closer to the nucleus. Across period 3, first ionization energy generally increases from sodium to argon due to increasing nuclear charge and decreasing atomic radius. However, there are small decreases between magnesium and aluminium, and between phosphorus and sulfur. These anomalies are explained by electron subshell structure and electron-electron repulsion in paired p orbitals. Down group 2, first ionization energy decreases because the outer electron is further from the nucleus and more shielded by inner shells. In this chapter, we've explored atomic structure, isotopes, electron configurations, mass spectrometry, and ionization energies. Mastering these concepts provides the foundation for the rest of A-level chemistry. Thank you for watching.